Come to this world.
Ah.
Blind.
Hello, can you guys hear me? Okay, we can wait like 2 or 3 more minutes just for everyone to get in, and then we'll get started. Or actually, in the meantime, if anyone's not in the GitHub organization, could you guys please like speak up so we can add you guys? Okay, do you have a GitHub account? If you can just give me a GitHub username, I can add you right now. Just give me the username. You can type it for me, and I'll just add you. And if you guys got an invite for the GitHub organization and you haven't joined yet, there's still 10 invites that haven't accepted. So if you guys can, that'd be great. But whoever was saying that they weren't in, could you give me your account name, please? Okay, Ishan, can you make one then? Can you make a GitHub account? Just go to github.com and create an account. It should be pretty simple. And then give me your username after you're done with that.
I have a quick question.
Yeah.
Okay, so basically, I was in the last class when you guys sent the email and I joined, but for some reason it kicked me out of the team. Like, I'm not in the team anymore.
I can just give me your username. I can add you again if for some reason that happened.
I'll just type it in the chat.
Yeah, that'd be great. Okay. Yeah, I got Shrish's then. Let me add you. You should probably get one too. Yeah, you'll get an invite. You'll get an email notification saying that you are invited. But okay, yeah. So once you send that, I think we'll just get started. Okay, I got it. Okay, got it from you. Oh, okay, it says you're already in the organization. Are you sure you're not in?
Me?
Yeah.
So I'm in GitHub right now, and
Yeah.
it says your teams, and it says you don't belong to any teams yet.
Oh, okay, that's not the right place. Here, just go to this link. Go to this link. I dropped the link for you, and then you're in. So you're good. You're good. Don't worry.
Oh, okay.
It's an organization, not a team, so it's a little different. But yeah. Okay. Anyway, so I'm not in yet. Here's my okay. Let me add you real quick. And just for like, we'll get started now. But if you guys aren't in the GitHub, just drop your thing in the chat, and we'll add you guys. So today we will. Viraj, you want to get started with? Yeah, just send me your emails if you guys aren't in it. Viraj,
Have we done
Yeah,
the
could you
repository
share?
thing yet?
Yeah, don't worry about creating a repository right now. If you haven't created one, we can create it later. There's no rush, but yeah.
Ian, do you want a screen share or do you want me to?
You can start because you're gonna.
Yeah, sure.
But okay, basically for today, we're just gonna talk about like the theory and like the concepts for machine learning, and we're gonna talk about two things. We're gonna talk about regression models, and we're gonna talk about deep learning. So if you guys remember what deep learning was, does anyone remember what deep learning was from last class? If you remember, just like shout out. Okay, well, basically deep learning was it's basically creating a machine learning algorithm that is like similar to the human brain, such as it has neurons and nodes and lots of those things. It's basically the same structure, but we'll start with linear regression because I'm sure a lot of you probably understand the concept. Are any of you guys like? How many of you have not taken Algebra 1 yet? Could you just like type in the chat?
You guys like click the raise hand button or something?
Yeah, just click the raise hand button if you haven't taken Algebra 2 yet. Or Algebra 1, sorry. Algebra 1.
Okay. Yeah.
Algebra 1. Okay. What grade are you guys in? 6, 7. So you're going into 7th? Or are you guys going?
Or
Oh, yeah, that's fine. We'll make it very simple then. Don't worry.
does that mean going to or
Yeah, going
Yeah,
to.
yeah. Just like what grade are you guys going to go into?
okay?
Okay, cool.
Yeah, okay. That's good then.
I'll gloss over more of the
Yeah,
mathematical
Ruchi,
parts.
I'll add you to the organization. Okay, Viraj, you want to get started?
Yeah, let's go.
You
One
can screen
second,
share,
let me just
right?
screen share.
Yeah.
Okay. Can you guys see my screen share?
Yeah.
Okay, cool. Okay, so today we're going to talk about linear regression. And linear regression, the definition of it is using supervised learning, which we'll cover later in today's class, to determine a linear relationship between the x variable and the y variable. So basically, the way it works is first you're going to plot the two variables together. So you create a simple graph. I'm sure all of you guys have seen this before. And then you're just going to come up with like a starting hypothesis function, something you think will work reasonably well, right? And then you're going to plot that. And then some of you who've taken Algebra 1 might know what a line of best fit is. Essentially, it's a line that you think will match fairly well with the data you were provided. So you can see the line is going through and matching relatively well with the data provided here in the graph. And next, you're going to find the error margin between each of these points. So for example, right here, the line thinks that the y variable would be right here, but instead, with that independent variable, the y value is up here. So you're going to do that for each point on the graph, and you're going to add all of them together and find the average. So you basically find the average of how wrong your function, your hypothesis is compared to the actual data. And then using this information, you're going to use a little bit of calculus, which you guys definitely don't need to know for this class, to kind of minimize that error. And you're going to keep repeating that process of slowly going down and down and down and minimizing the total error to reach the best possible correlation you can with the data. So,
and so if any of you guys don't understand anything we're talking about, just speak up or write a comment. There is like, you guys are like pretty young, so you might not know all of this, but
I know it might be a little overwhelming, but at its core, it's pretty simple. So, and also, could you guys like speak up and unmute, because like I can't see the chat. Anyway, so we're gonna focus more on the math aspect of it rather than the coding aspect, even though at the end, I'm going to show you what it would look like if you were coding machine learning algorithm. And there are two main ideas you want to know with linear regression. First, there's the cost function. And
Roger, they're asking if you could explain it again real quick.
Oh, okay. Yeah. Okay, so linear regression is basically where you're trying to map the hypothesis function you come up with to a set of provided data that you get from like a data set or something. And the way you do this is first you come up with like a starting function, like a hypothesis, like you would do in any sort of scientific area. And then you're going to find how wrong your hypothesis is compared to the actual data. And then you're going to take some steps to try and decrease that error that you come up with. And you're going to keep repeating this process until you gradually reach the best possible correlation you can with your data. So if you see on this graph, you can see that it's going through the data pretty well. It's going in the middle of it. But for example, but it took some time to reach this. And your machine learning model is basically to make this line match as well as it can with the surrounding data. Do you guys have any questions about that?
If you guys don't understand, just please speak up. It's the best way to make sure that everyone understands anything.
I have a quick question.
Yeah, what's up?
So why are they like on different sides of the line? Like, what does that mean? Does it mean anything?
Oh, well, obviously you can't go through each individual point because they're all scattered in different places, right? And so what you're going to do is you're going to try and get them and get the line as close to each individual point as possible, right? So, and to do that, you have to make some compromises, and this line is the best way you can get as close to all the data points as possible. Did that make sense, or?
So basically, in like a data set, right? You have coordinates basically, and use like there's some coordinates will be above the line and some will be below the line, and you're just trying to create the line that is the most accurate and the closest to it, right? Like, so let's say you like in a regular line you have like, let's say you have like a line like 0 0 1 1 2 2, right? That's going to create like a straight line with like y equals x. That's your like linear line, right? But when you have a data set, you don't obviously have a straight line always, and that's why you have to approximate a line.
Yeah, exactly. Any more questions?
I joined a bit late. Can you just explain what linear regression is?
Yeah, sure. Linear regression is basically a way where you create a linear relationship between your x value and your y value, and you're trying to match your relationship the best you can to the data provided. So this is how you do it. Basically, you're going to you're going to come up with a starting hypothesis function, which is just like a straight line on your graph. And then you're going to measure how well it matches with the data provided, like how off it is from each point. And using your data from how much error margin there is between your actual data and what your function thinks will happen, you're going to basically change the line to minimize this error margin, and then you're going to keep repeating that until gradually you're able to decrease the error margin until you're at your lowest error possible. I know it might be a little overwhelming right now, but as we go through and like go into these steps one by one, you guys can see that it's actually pretty easy. Are we good? Cool. Okay. So this is called the cost function. It looks really intimidating, but essentially what it's saying is that let me start over. Sorry. The cost function is basically a way for you to measure how well your hypothesis function matches with the data provided. And what it does at its core, it takes the average difference of all the results of your hypothesis and compares it to what the actual data is. So right here, focus on this graph because this is the actual core of the function. So if you guys see in here, the HO xi minus yi, it's basically comparing each y value of the function of your hypothesis function to the actual data provided. So by subtracting one from the other, you're able to find the difference between them and therefore find the average error. Does that make sense? Okay, good. And this line, this symbol, those of you who've taken algebra will recognize it. It's called a sigma. And basically what it does is for each entry in your data set, you're going to cycle through that and add all of them together. So for example, if you have 4 entries in your data set and your hypothesis says it'll be 1, 2, 3, 4, but the actual data will be 1, 3, 5, 7, right? And so for each data point, it'll find the difference between what the actual value was and what the hypothesis value was, and it'll add all those errors together. Do you guys understand that? Okay, good. And so now at this point, you have all the error in your function added together, right? But you want to find the average of that data. So what you do is you basically divide the entire thing by how many training training examples you have. And so we categorize that as M. We represent however many of those you have as M, and you divide this total error by M. And so what you end up with, what the cost function basically gives you, is the average error of your hypothesis function compared to your actual data. So the cost function, that is basically the core of it, and it just results in a average error for your hypothesis function compared to your actual data. Do you guys have any questions?
Yeah, please ask if you guys don't understand. That's the like just say it out loud. That's the best way to make sure you guys understand.
Sorry, I don't really understand the equation, like the here's what you should actually focus on. I don't understand like how that ties into your line and minimizing as the dots as close as possible,
sure.
like minimizing the errors.
So just for reference, the equation is actually not as important. I'm just trying to convey to you guys the mathematical aspect behind it. But basically, you guys can see my cursor, right?
Yeah, I can see it.
Yeah, we can see.
Okay, cool. Okay, so you guys see the part inside the parentheses here, right? So imagine this as what your function thinks, right? This HOXI is what your function thinks is the right y variable, right? And your yi is what the actual y variable is. So you're subtracting what it thinks the y variable is from what the actual y variable is. And by finding the difference between the two, you're able to find the error. Does that make sense? I'm not done with the explanation yet, so I'm just like asking if you got that part.
Yeah, I got that. Thanks.
Okay, cool. And I'm not sure what grade you're in. Do you know what the symbol means?
No.
Okay, so basically what it does is this symbol allows you to cycle through, because you're finding the error of 1 point on your data set, right? But you have like however many entries you have. You have, let's say, 47 entries in your data set, right? So you need to do this for every entry in your data set. You need to find the error for every entry. And so what this symbol lets you do is you add together the error for every entry and compile one number, right? And then, but you want to find the average among that. So then you divide by however many data sets you have. I mean, by however many entries you have. And then with that, you result in whatever the average error would be. Does that make sense?
And again, at the end of the day, it's just basically what you want to do is you want to create a line for the data that you have. You just want to create a linear line. It's basically that's it. And if in Algebra 1, I know you guys use Desmos. Like if you guys ever do Desmos, you create the line of best fit. That's essentially what you're doing here. It's just you're doing it in code. And it's really important for different types of data sets.
But again, if you guys don't understand the equation, it'll make sense as you go through. But at the end of the day, you don't need to know the mathematical aspect. Like you don't need to completely understand it before actually using it in code in reality. Okay, so the next topic we have is gradient descent. So at this point, you've found the average error in your function, right? So your hypothesis, you've compared it to your actual data, and now you want to improve your hypothesis. So what you do is you don't need to, this uses a little bit of calculus, so you don't really need to understand that part. But basically what you want to do is you want to find a method to decrease the average error in your function, the number that you came out with at the cost function. And so this graph right here, it's a visualization of what the average error is. So at the top of the red hill, that would be like if you had a really, your error with your hypothesis versus your actual data, that would be really, really high. And down here at the dark blue, that would mean that your data is very, very correlated with your actual hypothesis. And so what you want to do, as you can see it going down, you want to get it down this track and to the lowest error possible, right? And so what you do is you use a derivative, and you guys don't have to understand that, but basically you're trying to decrease this, right? And so what you do is you use something called a learning rate, which is each individual step down this graph and trying to get to the bottom of the function and trying to get to the bottom of the graph. And so imagine this is your imagine this is a graph of your data. So this is where you start off with, right? This is your initial error, and then you're trying to go down. You're trying to go down the error graph and try and get to this global minimum, which is the lowest your error can possibly get. And at that point, you've come up with the best ML model you can. So you put the cost function and gradient descent together in this equation, which again, you don't have to understand, but basically you take the cost function, which is right here, you multiply it by a learning rate, which basically tells you how fast you go down that graph I just showed, and then you subtract your new value from your old value. So this is a fundamental concept in programming, the whole idea that you take your error, you subtract it from your old value, and you come up with a new value. And you just repeat this again and again until, again, you get to the global minimum, the lowest error your function can get to. Did that make any sense? Do we have any questions about that? So just to clarify, by decreasing the error of your hypothesis compared to your data, you're increasing the accuracy of your function, which is basically the entire point of machine learning. You're learning from your initial data. Any questions? Okay, cool. So here is an example. We're not going to use it. What was that? I couldn't hear you, sorry.
Can you go over the gradient part again?
Yeah, sure. Okay, so basically at this point, you have a cost function that can basically tell you, it outputs how much your error margin is between your actual data and the hypothesis function you came up with, right? So you have that information and you want to decrease the error margin that you came up with. You want to get the error as low as you can because that increases the accuracy of your function. And so what you do is you essentially use a learning rate that tells you how far, that tells you the direction you have to go to decrease your error margin. And you run through this thousands of times until you finally get to the lowest you can. And so this is just a visualization of what it would look like. So let's say you start over here, right? You have a very high error. That's why you're on the top part of this graph. And using this learning rate, you're trying to go down. You use the cost function as a measurement, and you try and decrease your error until you can go down and down and down and down until you're at the lowest point possible. So this involves a lot of calculus, but the basic point of it is that you are able to decrease the error of your graph, decrease the error between your hypothesis and your actual data to minimize your error. Is there any question?
They're just two numbers. Don't worry about it. It's just like two variables. They're not the letter doesn't really matter.
Oh yeah, it's like if you have a y equals mx plus b, it's just.
And the function j is the cost function that we're using. Don't worry about what the actual cost function is, but yeah.
Just the important thing is that you guys know the concept behind it. So the cost function is a way to measure the error of your hypothesis, and gradient descent is a way to decrease that error. That's all you guys have to know for the most part. So I know that was a lot of math, but in this example I'm showing right here, we're going to see how we could actually apply that to a machine learning project. And I'm not sure if you guys have ever seen actual machine learning in like Python before. So I'm just going to go through it with each individual cell. So right here, you're going to
Panda, you're not even looking.
Yeah. Pandas.
Yeah.
I mean, you're good.
Anyways, so Pandas is basically a Python library that lets you do really advanced computational tasks, like math level stuff. And so what we're doing right here is we're importing pandas, and that allows us to use all the features that pandas has to offer instead of us having to come up with them manually. Right here, this line, we're basically telling our function that we want to use that data set. We're bringing them together. And with these two values right here, the x value, you guys saw on the graph multiple times that x is our independent variable and y is our dependent variable. So we're just like initializing these data sets. And I just realized, I'm very sorry, I forgot to explain what our model does. Essentially, our goal right here is to predict the salary of an employee based on how many years of experience they have. And for our purposes, we're going to assume this is a linear relationship. So if you have more years of experience, you have a higher salary, which usually makes sense. And so the x value right here would represent how many years of experience you have, and the y value, which is dependent on that, how many years of experience you have, would be the salary. Do we all get that? Okay, cool. So usually when you have a data set, you first want to train it, and then you want to test how well it works, and like have a value of my model is like 70% accurate, for example, okay? So right here is where we split the model into, we split our data set into two different sections. So the first section, which we call a training section, has 66% of the data set. It has 2/3 of it. And then we leave 1/3 to test our model afterwards, after training our model. Right here, sklearn, this is probably the most important data set. This is the most important model. I'm sorry, the most library for machine learning. And as you can see right here, from sklearn, we're going to import linear regression. So all the functions that come with linear regression, we're going to make them available to us, which is much easier than having to replicate that whole mathematical thing above. And right here, you see we have regressor and linear regression, and then we use that regressor to train our model. This is exactly the point where we train our model. We take all the data we have, we apply it to our hypothesis model, and we try and decrease that error margin. Then right here on step 4, we're going to do the same thing and use that model we just made to predict how well our model is, how well our model can predict information. So we just test the accuracy of it. So we'll say like it's 80% accurate, for example. And this is another important library. It's called matplot, and it's basically a way for us to visualize what is happening behind the scenes. Because right now, as you guys see, there's no output that is relevant to us right here. We can't actually see how well the model is doing. We can't see any of that. What was that? Okay. So we want to visualize these results, and matplot is basically a way to implement all this data into graphs and stuff. And so right here, this data basically creates this graph, which shows how well our model matches to the data. So the red dots right here, that's the actual data. That is what we got in our data set. And the blue line right here, that is our model. That is our model that we created. So you can see it actually matches pretty well. It's actually going through some data points, and the data sets are evenly regulated on both sides. And it actually looks pretty good. So we're happy with that. And so we see how well our model matched with the training data, which was what it was trying to decrease the error margin with. But now we want to see how well it will work with data we haven't seen before, right? The prediction data. And so what we're going to do is we're going to plot the actual, the prediction data right here, the testing data, and then we overlay the same line that we had before. So we put it over here. And we can see it actually matches pretty well. It actually goes through a lot of points, and it's fairly close to everything. So we're happy with that. And then just to see how it would be practically applied in the real world, here's an example. So we're just going to print the average salary of a person with however many years of experience you want. And we can see right here, we got outputted the predicted salary of a person with 15 years of experience is $167,000. And so that's basically linear regression. Just to go over it again, because I know that was a lot. First, we're going to come up with a hypothesis function that tells us that we think will match fairly well with the data. Then we measure how incorrect our hypothesis function is compared to the data that we received. Then we basically take steps to decrease that error margin through gradient descent and trying to kind of go down this graph we showed. And eventually we want to reach this low point, which is basically saying this is the lowest error margin we can go. Do you guys have any big questions or anything like that? Anything not make sense?
I'll
Can
ask
you
now
go
because
over the steps 1, 2, 3, 4, 5, 6 again?
Oh yeah, sure. So first we want to plot the dependent variable against the independent variable, which is like we show here. You're just making a simple graph of how the model would look, of how the data looks, right? And then you're going to come up with a starting hypothesis function. So let's say you come up with this line right here that we think will match fairly well with the data, right? Does that make sense?
just keep
Okay.
going.
Cool. So then using the cost function, which you guys don't need to know because the math is very complex, we're going to come up with the error that your the error between your hypothesis and your actual data. So right here, for example, if the model thinks that our y variable for this x would be right here, right? But the actual y is up here. And so we're just trying to make that into a number and find the average error between all these data sets and the actual function, right? And so we have that data and and then using gradient descent, we want to basically decrease the error between them. And we keep doing this again and again until we reach the lowest it can be.
Okay, so I think that's good for linear regression. Again, if you guys have questions, we will. This notebook is in the GitHub repository, and again, you can just ask questions in Slack. We do need to move on to the next part of the class, but yeah, hopefully everyone understood that. So I think I'll take over now. Okay, Raj, you want to stop screen sharing?
Yeah.
Okay. 1 second. Let me. All right. So you guys can all see my screen, right? Raj, can you see it?
Yeah.
Okay, great.
You can see it.
Okay, so let's just hop it right into it. So basically, again, this is from day one. From last week. We went over this. We know what machine learning is. It's the practice of using algorithms to analyze data, learn from that data, and then make a determination or prediction about new data. So machine learning versus traditional programming. One example is analyzing the sentiment of popular media outlet and classifying that sentiment as positive or negative. So if that's like saying, let's say I wrote a sentence. If I gave you if I said something to you, you have to say if it was like a positive sentence or a negative sentence. And so traditional programming, you would have to look at the words associated, and then you have to write conditional statements. But that's like creating a lot of if statements, right? But machine learning, you don't have to do any of that. It's all automated and it's all very simple. And it all does it in one look because you just give it a lot of data, and the model itself and the algorithm itself knows what is positive or negative. And again, we went over this artificial intelligence, the big sector. Then we have machine learning, and then lastly we have deep learning. And yeah, so let's talk about deep learning. We went over what deep learning is, but basically the definition of deep learning is it is a subfield of machine learning that uses algorithms inspired by the structure and function of the brain's neural networks. So in your brain, if you guys know any sort of neurology, you have like lots of neurons and neural networks. So that's what we try to imitate with a machine learning model, with that deep learning model, sorry. And as a subfield of machine learning, deep learning is also uses algorithms to analyze data, learn from that data, and then make a determination or prediction about new data. That's clear with everyone, I hope. We went over this last class, so I think that's good with everyone. Yeah. So let's keep moving. The next part is there's two types of machine learning. There's supervised learning and there's unsupervised learning. So supervised learning occurs when your deep learning model learns and makes inferences from data that has already been labeled. And then unsupervised learning occurs when the model learns and makes inferences about new data or about unlabeled data. So what does that mean? Basically, let's say I give it a picture of a dog. I have to give it a label. For supervised learning, I have to give it a label, and that label will say it's a dog, right? And then for the model itself, it'll be like a number, right? It'll be like one or zero. Let's say, like in this situation, we see that we have a dog, we have a picture of a dog, and it's labeled a dog. A picture of a bird, and it's labeled a bird. Airplane, and it's airplane, right? So it's basically you have to give the algorithm a label so it knows what it is. But for semi-supervised learning and unsupervised learning, you have some of the data is labeled, but some of them don't have a label. And that you have to do things such as clustering and grouping based on features and attributes to figure out what is what. And that's a lot harder. We won't be doing that in this class. We'll just be doing basic supervised learning. So basically, it's just you have to give it a piece of data and has to have a label to it. Is that clear with everyone? Yeah, okay, great. So yeah, one example of like labeled is classifying images of dogs and cats, where you would have like a label that would say it's a dog or a cat, or you don't have any labels and it has to figure out based on features. Whoops. Okay, let's move on. So basically we have an artificial neural network, right? And an artificial neural network are deep learning models that are based on the structure of the brain's networks. Basically, it's just your brain's network in a model, and it's artificial, right? That's like why we're coding it. And it's basic, it's to replicate that. And some other terms that you might hear neural net, network, like net, model. Those are all the same thing. They all pretty much mean the same thing. So neural networks are computing systems that are inspired by the brain's neural functions, and these networks are a collection of connected units called artificial neurons, or neurons, right? And each connection between neurons can transmit a signal from one neuron to another. Let me scroll down so you guys can see it. The receiving neuron processes the signal and signals downstream neurons connected to it. So basically, if I'm one, like right here, we see like a dot, right? So each one of these is a neuron, and we pass on a signal to the next one, and you go on to the end, right? And basically, the neurons are organized in layers, and there's different types of layers. There's an input layer, which is basically where you would give the image or the text or whatever data you're using. Hidden layers, which transform that data to get an output, and then there's an output layer, which usually is just two outputs for like a binary classification. And these signals are sent from the input layer all the way to the end. And this is like a picture, right? And then each neural network, each neuron is a circle, and there's many different layers. Here we only have 3. So here's how you would code it. Basically, there's a package called Keras, which is from TensorFlow, which is from Google. It's just a package for machine learning. And basically here we're creating a model. We're calling model is equal to sequential, which is just a model type. And then we create the layers, right? The first layer is a dense layer, which is the input layer. And basically it has the shape of the input, which is 10. And then the second layer is this. And we'll talk about activation functions in a second. So is that good with everyone? I don't see any questions coming in. Okay. So let's talk about layers. Artificial neural networks are typically organized in layers, and different types of layers include, you'll learn about these different types, but these are a couple. Dense, which means fully connected. Convolutional layers, which we will actually use later in a few weeks, and those are for images usually. Pooling layers, recurrent layers, normalization layers, and there's many different layers. And there's different layers because each node in each layer does a different type of transformation on its input, and some are better than others. And so just convolutional layers are better for images, and recurrent layers are better for time series data. And each node in a layer represents an individual feature for each sample within our data set. So let's say I give it a 4x4 image, right? It has 4 pixels by 4 pixels. That means I need to have 16 input nodes, because each node will take in each pixel. And then each input is connected to another node in a hidden layer, and the input is then transformed into another output. And then each connection here, like the connections between each node, it's called a weight. And this is just a number between 0 and 1. And it's the strength of the connection between a node. The input will be multiplied by the output. Input will be multiplied by the input, and then the weighted sum of each weight will be calculated, and that is passed through our activation function that will transform the result from a number of 0 to 1, just on a per neuron basis. And that result is then passed on to the next neuron of each layer, and it keeps going to the end. And the model learns how to adjust these weights so that it's optimized and can make the best predictions. That's using optimization, and that's using the activation function. And the last layer contains as many nodes as there are classes. For example, if I was predicting a drawing that has like numbers, right? It was 0 to 9, there would be 10 nodes. And if it's just a picture of cats and dogs, there'd be 2. So this is another example. So each weight is a number. And we can see that, let's say the input we started with was 1. And then so basically what it would do, it would pass on to this node, right? And this node and this node. So we can do the quick calculation, right? 1 times 0.9 is 0.9. Then this is 0, obviously. And this one is 0.1. So then this value is going to equal to 1. And that keeps getting passed on to the end. Oh yeah, so the initial weights are completely randomized. They're just completely random. And basically every time you, so we'll talk about training in a little bit. But basically as the model sees more data, it learns how to change those weights to make the be better for the certain classification problem. So here's how I would code that, right? So basically it would just be, 2 layers, activation functions. I'll talk about that in a second. We went over this. And this is just another picture of a neural network. Is that good with everyone? Okay. So let's talk about activation functions. In an artificial neural network, the activation function of a neuron defines the output of that neuron given a set of inputs. So the activation function takes the weighted sum of each connection and passes it onto an activation function. So over here, in each of these nodes, we run an activation function. Whoops. Okay, my bad. But basically, each thing we're gonna run a in each node we run an activation function, and that's how we create our transformation, right? So an activation function. So basically, here's the equation. You take the output. The output is equal to So you take the weighted sum of your inputs, which we talked about, right? And we put that into the activation function, and we get an output, and then we pass that on to the next layer. So one example is sigmoid. This is what sigmoid looks like. It's just basically a function. So let's say it came with an input of 0. It would just output 0.5. And if I gave it 2, it would be something around 0.8, 4, etc. Right? And this is what these functions look like. This is just one example. There's lots of different ones, but sigmoid and ReLU are usually the ones that you'll use. And since they're biologically inspired by the activity in our brains, when different neurons fire or activated, they are activated by different stimuli. And so like an example in the real world is if you smell something nice, it'll fire certain neurons in your brain to give you a certain reaction. That's the same thing here. You give it a certain number and it will trigger something and it will give you another output. And neurons are either activated or not activated. And so basically it's a 1 for activated and 0 for not activated. And the closer you are to 1, the more activated, and the closer you are to 0, the less activated that certain node is. And it's not always a 0, like a -1 to -1. You can have different, like ReLU down here. Follow me this. Like ReLU, it sees that it's from 0 to 1, 0 to 1. And so if you have a negative number, it's just going to output nothing. So this is how you would initialize an activation function. You would just type in the activation function name. There's lots of different ones. The ones we'll be using are either sigmoid or ReLU. And yeah, this is another way to add it in the code. Don't worry about the code too much right now. We'll talk about it more later. Does that go with everyone? This is like the really basic introduction of the basic ideas of like how a model is working. Like, so weights, does everyone understand like nodes, neurons, weights, activation functions, layers, what a model looks like? Please ask now because we are going to move on. If you have any doubt, just ask, clarify. It's better that you clarify now because later it'll be a little hard to catch up.
So
Can
you
you just
have
say what's the weight again?
Oh, sorry, what was it?
Can you just explain what a weight is again?
Yeah, so basically, think about it this way, right? Let's say we have inputs, right? A weight is basically, do you see how each node right here is an input, right? It's like a different number that you're inputting. And basically, you have to connect it to each node in the other layer, the next layer, right? But you don't always want the connections between two nodes to be like really strong, right? So a weight is basically how strong is the connection between one node to another, right? And sometimes you want those connections to be really strong, and sometimes you want them to be very weak. So basically, it's 0 to 1, right? And 1 means really strong, and 0 means no connection at all, right? So somewhere inside it, it's like a percentage essentially, right? So right here, this is like 90% connected. That's what it means. And basically it means that when we're training our model, we want these two nodes to be really close to each other. We want them to be, we want them to activate a lot. Does that make sense?
Yeah, thanks.
Okay, cool. Great. Any other questions?
Can you
Yeah, go ahead.
explain the activation part and the layers part?
Yeah. So a layer, right? You see how there's input layer, hidden layer, output layer, right? Basically, we're taking our inputs, we're transforming them with the hidden layers, and we're getting an output, which is 0 to 1 for classification, right? Layers are pretty simple. Does that make sense? And there's different types of layers, right? Like input, hidden, output. Those are the 3 basic ones.
Can you go over the code, these?
I think code is not that important right now because we'll go over it in a couple, like in a week or two. So I think since we are like a little short on time, we'll do the code later. But it's better that you understand the concept now, and we'll do the code. The code is like a lot easier to understand once you get the function, the idea. But okay, yeah. So you're saying So you said classify a picture of 100 by 100 pixels. You need million. Yeah, you need lots and lots of neurons, right? So this is like a really like very basic concept where only have 3 inputs. But let's see, if you had a 100 by 100, you have to have about 10,000 different inputs for each pixel, basically. Okay. And then activation functions is basically a transformation, right? So you have to take this number and do something with it. And basically the function, it was very similar to what we had in the linear regression. We have to change the value that we're getting, and we have to do some sort of calculation to it. Yeah, each circle is a node. Yeah, that's correct. So basically what we're doing is we're taking each input, we're taking input and we're putting it through some sort of mathematical function and getting a new output. And the function itself doesn't matter too much at this point, but basically it is important because you have to do some sort of transformation. Yeah, so in this picture there are 7 nodes. There's 3 in the input layer, 3 in the output, hidden layer, and 1 in the output. Is that good with everyone? I think we should talk about training before we finish. Is that good?
I have a question.
Yeah.
So for each like pixel, like the example that was talked about earlier, there would be 7 nodes.
No. So each pixel in an image is 1 node, basically. So let's say if I had a 10 by 10 image that I'm putting through my model, I need to have 100 different nodes. Does that make sense?
Yeah.
Yeah. So each pixel is a node, and basically, so if you might understand like how bright an image is, right? That'll be your input, right? For example, that's just one example. But let's say like on like insert 0 to 1, it's like 1 is really bright. It'd be like 0.9, and basically like that'll be your input, and we do something with it. We weight it, we pass to another one, and we transform it, and we pass it out. Does that make sense?
Yeah.
Okay, great. Pre-processing, we can talk about this later. This is not that important because it's just it is just about data, which is code. We'll talk about the code later. But here's what training means. Basically, training, you have to solve an optimization problem at the end of the day, right? So you have to change the weights. That's the goal, right? You have to change your weights in your model to create the best model that will always give you the correct output. So you do that using a optimization function, which is called stochastic gradient descent. And that basically means you want to minimize your loss, right? And optimizers can change the value of the weights based on what it learns. And the objective is to reduce a loss function. And Viraj talked about the loss function. You guys saw the little curve thing like that one like this. And basically you want to minimize that, right? We'll talk a little about it more later, but basically you give the model data and labels. If you give it a picture per se, it'll either predict 0 or 1. Then you tell it the real value, and then it knows how much it needs to change, right? So let's say you give it a picture of a dog. That'll be label 1. And then with our function, we're guessing, let's say we're guessing like a 0.6. Now we know that we're about 0.4 off, and we know how much we have to change our weights to adjust our model to be more accurate later. So that's the goal. And the loss is the error of what the model is predicting against what the image really is. So it knows how and what it has to change to get closer to a 0 loss. So basically at the end of the day, what you want is you want your model to be predicting 1 if the label is 1 and 0 if the label is 0. And the more data that you have and the more times that you give the data, the more that your model can actually learn and how to change its parameters and weights. Basically, each time you train, you're adjusting your parameters and you're adjusting your weights, and your nodes, you're changing your functions. And it originally starts with completely random weights, as the question earlier, and it changes them progressively. And the model will compute the gradient of the loss function or the derivative. Don't worry about this. This is like really high calculus. I probably don't even understand this. Okay, yeah. Yeah, so the objective is minimize the loss function. Again, Raj went over this. This is the same picture we had earlier. And I guess the last thing we'll do before we head out, we'll talk about a loss function. We'll talk about learning rates and loss functions. Just give me like 5-10 more minutes, guys. Let's just finish this up because we started a little late. So a learning rate is just a way of reducing the, Raj talked about this. It's just a way of reducing the gradient. So it makes incremental and small adjustments. And this equation shows what you're going to do. So you take the value of your loss over the value of your weight and you times it, multiply it by your learning rate. And your learning rate is usually something between 0.01 and 0.0001. And setting it too high, it might overshoot and you might pass the minimum of the loss function. But if you do a lower learning rate, it might take a long time to decrease your loss, which you don't really have time for. Right? So, and this is how you do it in the code. We'll go over this a little later. But learning rate, just like think about how fast you want your model to like change its weights. That's really it. And then lastly, we'll go over loss functions. A loss function, the overall loss will be collected and based on the difference between the prediction the model gave and the actual label value, and you want to minimize that. So here's a really basic of what it is, right? So basically your error is equal to your output minus the true value, right? So let's say the output was 0.25, but the real value was 0. So that means your error is 0.25. You're about 0.25 off. And so one example of a loss function is mean squared error, which squares each error for each piece of data and then averages it, and that's your loss. There's lots of different loss functions with different equations and calculations, but they don't really matter right now. This is the same picture Varad showed you earlier, but at the end of the day, what you're doing is you're just taking the average of your losses and you want to reduce that. So yeah. And then I guess I think we should go over this real quick. This is really basic. So basically, let's talk. So does everyone have any questions about the theory? I want to quickly go over data sets as well, but does everyone get the theory behind learning rates and loss functions? You don't have to understand the math. It's not that important, especially at this level. But as long as you understand, the goal is to reduce your loss function. Does that make sense to everyone? Okay. So let's quickly talk about data sets, right? So there's basically, let's say I have a set of 1,000 images, right? That's my data set. But I need 3 different data sets usually, okay? And here's why. So there's a train data set, a test data set, and a validation data set. So a training set is used for the model to learn, obviously, right? You give it a piece of data, say an image, and it'll predict an output. You'll see the label of that output, and then it learns how to fix it. So let's say I will give 80% of my 1,000 images as training data. So that means I have 800 images for the model to learn on, right? So basically, yeah, that's the goal. Then there's next is the test and the validation set. The validation set is passed during each pass of the entire data, right? So let's say I pass all my data, right? My 800 images, right? Then I'll pass in my validation set, which is a smaller amount of images. And basically I'll test my model. I'll see how well it's doing. I'll see my accuracy, right? So I'll create predictions on each of those new datas, and I'll see what I get. And I'll see what my predictions were, and I'll basically get an accuracy, right? Was I correct or wrong? And this gives a good gauge of our accuracy on the model, since our data hasn't seen. And the weights of the model will not, but this is really important. The weights of the model will not be updated based on the validation set. It's just for you to see, right? And this is learned to see if your model is overfitting and underfitting, which we'll talk about later. Don't worry about that. And then the test set is unlabeled, and it's used to determine how your model is doing after it's completely trained. And basically, here's what it would be. So let's say we have our entire data set. We'll section some of it off for training, some off for validation, and some for test. And basically, real quick, we'll talk about epochs. So batch size is basically, let's say I have 100 images, okay, in my data set. So my batch size is how many images I want to pass at once. So let's say I want to do 10 images at a time. That means it will take 10 batches for me to get through all of the data. but that's obviously not enough, right? Just seeing for the model, just to see the images once is not enough. It needs to see it a lot of different times, and that's where your epochs come in. An epoch is basically a full rotation of your full set of data that you train in. So basically, every epoch you're putting all your data into your model, and if you do more epochs, the more accurate your data will get. But obviously, doing more epochs takes a lot more time and a lot more computational power. So you want to find the good number. So for this one, let's say it's 20. So what we can see is that on epoch 1, we're getting a loss. We're getting our loss value. We're getting accuracy of 49%. And our validation loss is this. And our validation accuracy is 50%, right? And then once we get to epoch 20, we see that our loss is significantly decreased, right? We see our accuracy has gone up a lot. It's now at 91%. And again, our validation accuracy is now at 97%. So basically, the more that you show, the more data you give it, the more it's going to learn. That's the basic idea. Again, think about like you're trying to teach a little baby something. If you show it like, let's say I show it a square and a triangle, right? The first time, like if I tell them what it is, they might be able to understand. But if I show it over and over again, they're going to understand it more. That's basically what we're doing. Does everyone understand that? So yeah, I think that's all we're going to go over for today. Yeah, we'll do the rest next class and we'll start getting into some code. Does anyone have any questions?
Yeah, what is epochs?
Yeah, so an epoch is basically, let's say I have 100 images. That's my data set. And I give it to my model, right? But let's say I want to show it the data more than just once, right? So an epoch is basically one training set, right? So you're basically one loop over the data. That's what you're doing. So basically, I would show my entire training set 20 times if I'm using 20 epochs. An epoch is basically one loop of the training set. Does that make sense?
Great, thanks.
Any other questions? I think learning the basics of this is super important. To understand all this. Again, if you don't understand, you guys can ask questions in the Slack. Or ask now, obviously, or you can look at the notebook in the GitHub, or you can just click on it and it will pop up for you. It'll show up.
I don't know why, but the Slack, it said that like it wasn't like available or something.
Yeah,
Oh,
someone else texted me that too. I can just drop an invite link in the chat, and that worked for the other person, so it should probably work for you guys too.
Okay, thank you.
Any other questions about the concepts? Because that's really important. If you guys don't understand the concepts, you guys really will struggle when we start coding. This is pretty high level, especially for you guys who are really young, just entering middle school. It is a lot. It's probably a lot to understand. It's pretty advanced, but you guys need to ask questions now.
Is there more than one regression model?
Viraj, you want to answer that?
Oh, right. Yeah, there are definitely more types of regression models. So linear is definitely a big one, but there's also like quadratic regression models. There are cubic regression models. Basically, you guys learn about a lot of that in Algebra 2, and I'm pretty sure a little bit in basic algebra. But yeah, there are other regression models.
So in this class, will we be using only linear regression model?
Yeah.
Yeah, linear is the basic one. We're gonna focus a lot on what Ian just explained with neural
Yeah,
networks and deep learning.
We're not gonna do too much linear regression because it is pretty simple. We're gonna do a lot more machine learning and a lot more deep learning. So if you guys have questions about this notebook, I saw you guys had a lot of questions about linear regression, but this is a lot more complex than that. So I'm a little concerned you guys don't have questions. What does CNN
What
stand
does
for?
CNN stand for?
Yeah. So CNN means convolutional neural network, and basically what I showed you, where was it? Layers, right? There's basically it's a convolutional is a type of layer, and basically what that does, it just changes the it's a different way of like taking your inputs and transforming them. We'll talk about it when we get to the code, but just understand how layers work. That's a lot more important. Are there any other questions?
Cool. I think we can end for today.
All right. Yeah. So I think we will probably finish up then. Is like last time ask questions. If not, ask in the Slack. Yeah. So I guess just for tonight, or for like this week, for just basically for homework. There is no really assigned homework, but please go over these notebooks. If you don't understand them, you're really gonna fall behind in the class later. Because as we said on day one, we start really basic, right? We're gonna ramp up really fast, considering machine learning is a pretty intense concept. It's not really, especially for you guys who are really younger. Don't worry if you don't understand a lot of it, even if you don't understand it now. If you get the basic idea, once you get older and older, you'll learn more. right.
Yesterday's Python recording should be on YouTube. You guys should
Or ask Shivam. We don't. I'm not involved in that. So just ask the Slack.
Yeah. All right.
Wait, so
should we end?
Yeah. All right. Then I guess we'll head out then. Thank you guys for showing up. See you guys next week then.
Bye.
Thank you. Bye.